So, okay, it's 12 noon. This is Math 465. And then this week we have homework of 1.1 and then 1.2 that is due. And then you can use, as I mentioned, you can use a paper like this. And this is a paper you can write. Okay. And then on the right top corner, you should write Math 465. And then your last name first, and then first name second. And maybe today's day or that day's date. So like April 17th, okay, you can write so. And then please submit it to the Blackboard. There's a Blackboard homework turn-in name Dropbox. So please use that one. And then you should take a picture of this guy, a picture, scan, and then make one PDF file, preferably. If you can, that's okay. But make a photograph or scan, then make a PDF file and submit it to the Blackboard. Okay. So first of all, they have a question on homework 1.1 and 1.2. Any question? Are you okay? No question? Looks like there are 18 students appearing. Any question?
I do have a question.
Yeah.
I'm not sure if you went over the last class on number 13 on 1.2.
1.2, number 13. Okay. Let's see. Number 13, reach hand 13 cards without replacement from a deck of 52. And then there is a number 13. So 1 to 13. Okay, this is number section 1, 2, and number 13, and then reach hand 13 cars without replacement from a deck of 52. 13 cars from a deck of 52 cars. Okay. Then everything part A, B, C, D, part A and B, or maybe part A. Okay. 5 space, and then 4 hearts, and then 3 diamond, and then 1 club, and this is the one. The hand has 5 space, 4 hearts, 3 diamonds, and then 1 club. Now, what is this probability? So probability is calculated. Then what is the denominator? The total number of ways to have 13 cards from a deck of 52. So out of 52, we have to choose 13. Okay? This is without replacement. So 15, choose 13. This must be the denominator. You agree? Okay, out of 52, we are picking 13 cards. So this is a number of ways. It's a total number of ways. This is a very big number. Okay. Calculator, yeah, without calculator, we can't handle this guy. Okay, now for the denominator. So we have to choose 5 space, okay, 5 space. How many such ways? We're choosing 5 space from 13 space, okay? From 13 space, we are choosing 5 space. Out of 13, we are choosing 5. So this is a number of ways, right? Out of 13 space, we are choosing 5 space. Now, same thing for the hearts. Out of 13, we are choosing 4 hearts. Out of 13 diamonds, we are choosing 3. 13 choose 3. Now, last one is a club. Out of 13, we are choosing 1. Of course, this is 13, right? This is 13. So this many ways. You don't have to simplify this. Do you want to simplify this? I don't think so. Okay, this is very informative. Okay? Informative means yeah, you are showing the ways very clearly. Okay, so right, you can write this way. Make sense?
Yes.
Okay, good. Do you want to know the second part also?
I think I got it now.
Okay, good.
Yeah.
Any other question?
But now on part D.
D. Conquer D. Okay. This is a 501 suit and 4 of another suit, and then compare one and well, what is the question itself? Okay, let me see the question itself. Okay, part D is
D.
1 to 13. D. Okay.
Mhm.
Suppose you are dealt 5 cards of one suit and 4 cards of another, with the probability of having the other suits split 3 and 1 be greater than the probability of having them split 2 and 2. That's a question, right? Then, if you part D, okay, part D. The probability is probability. This first one is choose 13 of 5 and then 13 and 4, and then other 2. Again, this part is 13 and 3 and then 13 and 1. Okay, this is same as the about P. And then other one is what? 13, 5 and 13, 4. They are same. Then we have to compare 13, choose 2 and 13 choose 2, right? Is that right?
Yes.
Yes. Okay. Then thing is this one and this one. Compare these two guys. Which is larger? Okay. That's it.
Oh, okay.
Okay. So you can see which is larger.
I think.
All right. Good. Any other question? Right. Okay. Then I can move on. Right. So number 13. This is the 1 to 13 is a section 1, 2. Okay. Section 1, 2. So now section 1, 3. Wait. 1, 3. Section 1, 3. Section 1, 3. And then in this section, we define the conditional probability. Okay. Remember this conditional probability. Conditional probability of A given B. Probability of A given B. Okay. A given B. Okay. This is the one. This is denoted by P of the probability of A given B. Remember this guy? How did we define this guy? This is a probability of A in a section B and divided by probability of B. In this case, we need to assume that P of B is positive. Okay, P of B must be positive. Otherwise, this is not defined. Okay. Under this assumption, we can define the conditional probability of the event A to be the fraction probability of A in a section B divided by P of B. Okay, and then as I mentioned, okay, this is sample space S. Okay, this is sample space S, and then this is A, and this is B. This is B. This is A. This is B. And now we're talking about space B. This is our whole space, and then A is which portion? Yeah, looks like this is a portion. A in a section B is this guy, right? This is a portion, part of part A. This is A, and then A is here within B. B is now playing the role of the sample space S. Okay? B is the whole world, and then A is which part? This part. So this probability divided by this probability B is giving you the conditional probability. And that's the idea. So B is the whole world, and then A is how much part of that one. Okay? That is a conditional probability. And then you have some properties of conditional probability. Okay, you did. So now next step. Okay. Next step is using this guy conditional probability. We can have a multiplicative rule. Multiplicative rule. And that is it's a conditional probability, and then using this guy, here's a definition. I don't think this is a definition, but the textbook is saying so, so I have to follow. Okay, definition. Actually, this is a theorem. Okay, theorem. Rather than definition, this is a theorem. Okay? Theorem. Very simple theorem. Multiplicative rule. Multiplicative rule. This is our title. And this is giving you how to calculate the probability of the intersection of two events, P of A intersection B. This can be calculated. Now look at this. Okay? Look at this conditional probability. Here we have P of A intersection B. If we solve for this guy, then this is equal to this times this, right? This is equal to this times this. And then we can switch B and A. So this is now A. This is B. This is A. Okay, we can write like this. What I'm saying is B given A. This is same as P of A intersection B over P of A, okay? Provided that the P of A is positive. We can write like this. We can switch A and B, okay? So this is a 1. So look at this guy. Look at this guy. This is equal to P of A times P of B conditioned by A. So we can write like this: P of A times the P of B conditioned by A. And this is true if P of A is positive. P of A is positive. I'm using this definition. Then we can write this probability P of A intersection B as the product of this and this, or this and this. Okay? So another way is if you write B first, okay, P of B times P of A conditioned by B. And this is true when P of B is positive. We have 2 ways. This is a multiplicative rule. This is a product of two things. So the product is expressing the probability of the common part A intersection B. This is a multiplicative rule. Okay. So then, very simple example here. Conditional probability is defined. Okay, like we did last time. Conditional probability is defined last time, and then that is defined in this way. Okay, and then a multiplicative rule is obtained from that conditional probability. So now here's the example. Okay, in the ball there are blue chips and red chips. There are 7 blue chips in a ball. In a ball. Do you like chips? Yeah, I like chips too. Yes, there are 7 blue chips, and then 3 red chips. In the bowl, there are 7 blue chips and then 3 red chips. And then we want to get 2 chips at random and successively. So successively means without replacement. 1 chip is taken, then we don't replace it to the ball, but another second one is taken successively. And so then what we want to do is 2 chips are drawn, okay, successively at random. And this is what we have to do. And then there are 2 events considered. 2 events. What events? A is the first one is red. A is the event. The first one is red. First chip is red. And B is the event that the second is blue. The second is blue. So consider these 2 events, and then we like to calculate the common event A intersection B. What is the probability of A intersection of B? Okay, this is and what is this A intersection of B? Okay? This is a question. We like to calculate the common event A intersection of B. What is that probability? Okay? This is the question. How do you calculate this? First of all, I'd like to ask you, what is the probability of A? There are 10 chips, right? 10 chips. And then out of 10, we have 3 red. So what is the probability of A? The first choice is red. First pick is red. So out of 10, there are 3, right? So 3 over 10, is that right?
Yes.
This is the probability of A. The first chip is red. This is the probability. Out of 10, there are 3. So this is a chance. Okay. Now, what is the probability that after I pick the red one, what is the choice? Well, probability of choosing blue one. After I pick the red one, then what is the probability that we pick a blue one?
Would it be 7 over 9?
7 over 9? Do you agree? Do you means all the other students agree? Why this is 10, 9? Because the one chip is already taken, so 9 chips are left in the ball. Right? 9 chips are left. And out of 9, there are 7 blue ones. So probability must be 7 over 9. Right. That's good. Okay. This is the one. Yes, good. So now you can say what? The intersection of A and B. This probability is, we can use the formula here. This is the formula. P of A times P of B conditioned by A. Simply, we multiply these two guys. So this is 3 over 10 and times 9 over 7, right? We can simplify a little bit. 3 is so 7 over 30, okay? So this is the one. You don't have to convert to decimal. This is the exact number. If you convert to a decimal, that's going to be sometimes approximate number. So this is the exact number solution answer. Good. Okay, this is for 2 things, okay? 2 events. Can we generalize this to 3 events, 4 events or more? The mathematics is one thing is given, okay, or established, then mathematicians usually consider its generalization. Can you get more? That's a usual idea. Every mathematician. If you don't think that way, then you can't be a mathematician. So generalize. Okay? One thing is obtained, then it's a special case. So we can generalize it usually. So try to consider generalization. We have 2 things, okay? 2 things. Now, what about 3 things? So let's consider it. Then what can you say about that? Then we have to consider the intersection of 3 events, right? And then write this as a product of regular, I think, what? Regular probability and then conditional probability. Okay. So now, first step is if you consider generalization, I'm gonna do this way. Okay. So A intersection B, and then intersection C. Now it looks like this is a common part of 2 events: this event and then this event, this event and this event. So we can apply the 2 events case. So if you write this guy, then this is gonna be what? Probability of this, probability of A intersection B times probability of C conditioned by A intersection B. Is that right? You can write like this. Do you agree? Please agree.
Yes.
Okay, good. Thank you. So this is in the intersection of 2 things, this and this. And then we can apply the 2 event case and then get this guy. The thing is, one more time, this is the intersection B. So we can rewrite this part as P of A times P of B in a conditioned by A. Is that right? 2 event case, we can write like this. Many times the last one, okay? P of C, and then conditioned by A intersection B. This is a 1 product of 3. Okay? Product of 3. one regular probability and these two guys are conditional probability. So intersection probability of intersections of three events is calculated as a product of these three. So this is a three case. Can you get more general case like n? Yes, we can do. Just I show the formula. Is A1 intersection dot intersection AN. Okay? The same intersection of n event case. And then this is a one given three case. So looking at this guy, then you can say P of A1 times P of A2 in a condition by A1, right? Next one, this is A3 conditioned by A1 intersection A2. Okay, still we have to multiply that. What is the last one? Can you imagine? Last one. This is the last one here, A, B, C, then last one. Last one is here, so it should be AN. Okay, conditioned by what? There's a intersection of two others. So intersection of n minus one others. So A1 intersection dot. Intersection S of n minus one. This is a general case. You can imagine this. And then this is proved by mathematical induction, probably. Okay, so not hard. So generalization is very interesting. You can do, and then you can prove actually. So try to think about generalization, then our math can be more interesting for you. Right, so this is generalization to n events. Okay, so then what's next? I need a example. Okay, need an example. This is from the textbook. Okay, we don't need a number, just example. We're given probability of A1, this is 0.3, and then probability of A2 is given by 0.2, and then probability of A3 is 0.2. Same thing as A2, and then probability of A4 is equal to 0.2. So it looks like A1, A2, A3, A4. The union of these guys are forming oh no, not necessary. Oh yeah, disjoint. A1, A2, A3, A4. Okay, these guys are disjoint. And look at the probabilities, 0.3, 0.2, 0.2, 0.2. The sum of these guys is 0.9, 0.9. Not the whole thing, but anyway, that's okay. Yeah, that's okay. We're missing 0.1 part, okay, 0.1 part. And we are given conditional probabilities, like B is another event, and then probability of B conditioned by A1 is equal to 0.6, 0.6. And then probability of B conditioned by A2 is 0.7. And then probability of B, okay, conditioned by A3 is 0.8. That's a picture. So then a question is, okay, under these assumptions, what is the probability, conditional probability of B conditioned by A1 union A2 union A3? Okay, we like to calculate this conditional probability. This is what? All right. Okay, then you use the definition. Okay, definition of this conditional probability. This is a fraction, of course. Okay, and this is probability of B intersection of the probability of event of A1, A2, A3, union of those three by definition, divided by the probability of A1 union, A2 union, A3. This is by definition. We got this. Right. And what's next? Equality sign is here, but I'm gonna write the equality sign over here. Okay. Should be aligned, vertically aligned, but we don't have the space, so I'm sorry. Usually I'm gonna write equality sign over here. Okay. Align, vertically aligned. This is not here. Okay. What is the numerator? Can you multiply? Kind of. What is the rule?
A1 intersection B.
Yes, right. So this is B intersection A1 union B intersection A2. Yeah, thank you. Yeah, this is the one. And then B intersection A3. Okay, good. It is a numerator. What about the denominator? We have an assumption. Okay, these events are disjoint. Okay? These events are disjoint. So this probability is the sum of each probability. Is that right? It's a P of A1 plus P of A2 plus P of A3 because they are disjoint. Okay. One more step. Okay, one more step. What about these events? Okay? B intersection A1, B intersection A2, B intersection A3. How about these three events? Are they disjoint? These guys disjoint? Yes. Yes. The picture is like this. A1 here, A2 is here, A3 is here. Somewhere we have A4. Okay. And then this is here B. Okay, B is something like this. Okay. Then this is the portion we're considering. A1, A2, union of A1, A2, A3, and then this is B. Then the common part is this. The common part is this is divided into this part and this part, and then this part, right? This three. So A1 intersection B, A2 intersection B, A3 intersection B. These three parts. They are obviously disjoint. So we can write numerator as the sum of each probability. B intersection A1 plus wait a minute. Yeah. This is a B intersection A2 and plus B intersection A3. Okay, we can write like this. And then denominator is of course we can add those three things. Okay, this, and this. This is 0.3 plus 0.2 plus 0.2. Is that right? Okay, we can write like this. So one more step. Okay, one more step. What is this probability? Common part B intersection of A1. We can use the conditional probability or multiplicative rule. This is a probability of A1 times the probability of B conditioned by A1. This is given. Probability of B conditioned by A1 is given. So we can write this as probability of A1 times of probability of B conditioned by A1. Okay, we can write this as the product of these two guys by the multiplicative rule. And also the second one, in the same way, P of A2 times the P of B conditioned by A2. And last one is a probability of A3 conditioned by, no, condition, this times, I'm sorry, this times B conditioned by A3, okay. And divided by this is 0.7, okay. This is divided by 0.7. So we can move on. Just a calculation. P of A1 is 0.3, and then times the conditional probability 0.6, and plus A2 is 0.2, and times the conditional probability, that is 0.7, and then plus 0.2 times dash conditional probability is 0.8. Yeah. And then divided by 0.7. Then I'm gonna write this 1.8, then 1.4, and then 1.6. 1.8, 1.4, 1.6, 1.6, 3, 4.8, 0.48 over 0.7. Can you get more? Best is 24 over 35. 24 over 35. This is the exact value. If you like, you can convert to the decimal, but this is not. This is a infinite. But this is a repeating decimal, probably. Yeah, if you want, then this is 0.6857142. Okay, and then this part will repeat. This part will repeat. This is the exact answer. I accept this. This fraction. Fraction is good. So this is how we calculate the conditional probability. Okay. Any questions so far? Okay. Next one is problem 134. 134 looks interesting. Looks interesting. So 134. Problem number 134. Even numbered question. Two cards are drawn successively and without replacement from an ordinary deck of playing cards. 52 cards are there. And compute the probability of drawing two hearts. Two hearts. Two cards are drawn. So this is indicating two cards are drawn successively from a deck of 52 cards, okay, without replacement. So then calculate the probability that the two hearts are obtained. Two hearts are obtained. Drawing two hearts. What do you think? First one is hard, and then second one is also hard. Then what is the probability that the first one is a heart? There are 52 cards, and then there are 13 hearts. So out of 52, there are 13 hearts. So 13 over 52. This is a probability that first card is a heart, right? And multiply the conditional probability. Condition that the first one is a heart. Okay? First one is a heart. And we want to draw another heart. So the situation is, how many cards left? One card is drawn from 52. So there are 51 cards left. Out of 51, how many hearts are there? There are 12, because one heart is drawn. So this part is a conditional probability. One heart is drawn at the first one, okay, first try. And so there are 12 hearts left, and then out of 51. So we multiply these two guys, okay? And then you can simplify a little bit. Okay, this is 1/4, and then this is 1/4, right? 1/4, and 4 and then 3 will cancel, and then 3. So will be what? Okay, 1/4 is this, and then times 12 over 51. Okay, and then we can simplify this a little bit. Okay, 4 and 12. So this is 3, and 3 and 51 is cancelled, and this is 17 and 1, right? So 1 over 17. It should be the one. Okay, this is a probability. 1/17. Two hearts are drawn. First one is heart, also second one is a heart. So this is a probability that first one is a heart, 13 over 52. One heart is drawn already, so there are 51 cards left, and also 12 cards heart left, so 12 over 51. Okay. Next one, okay, next one. What is a probability that first one is a heart, okay? A heart. Then a spade, no, club, like this. My picture is not good, but this is the one, okay? First one is a heart, and then second one is a club. What is this probability? First one is a heart, and then second one is a club.
What was it? 1/13.
1 over 13?
1/13 times.
Over 52, right? Out of 52 cards, and there are 13 hearts. And then second one is what?
13 over 51.
Yeah, 13 over 51. Do you agree? There are 13 clubs, and then out of 51, one card is drawn, so 51 left.
No, are we choosing one heart only?
Yeah,
Or-
one heart,
Okay.
and then club. One heart is chosen. The second try is a club. I like to have a club. This is a probability that one heart is chosen at the first draw. And then situation is changed. There are 51 cards left, but still 13 clubs are left. So out of 13, out of 51, we have 13 clubs. So the possibility is this. Okay. In this case, we can simplify a little bit. This is 1, this is 4. So 1, 4. And then we can divide this guy, right? So this is 1. So 13 over 4. So 204. Okay. This is the best possible. 13 over 204. This is the probability. Next one is not so simple. Okay. First one is a heart. Then an ace. Excuse me. Okay. First one is a heart. But next one is an ace. The second one is ace. There's a possibility that we can draw a ace of a heart for the first try. Okay, that's possible. Okay, so consider that one. Then how do you proceed?
Want to be like part B?
One is part B.
This will be 13.
Okay, if you do so, then what situation is heart is 13 out of 52. Yes, and then second one is
13 over 51.
It would be 3 over 51, right?
3? Why 3?
Because we can pick an ace from the hearts.
Yes, that's a possibility. But what about the 2 of the heart? Well, king of the heart is drawn. Then there are 4 is
So
Yeah.
4 over 50.
Oh, okay. So then it'd be 4 over
Mhm.
51.
4 over 51.
Yeah.
This is it?
Mm,
Really?
I think so, because there's only 4 hearts
Yes.
with the cards.
Okay.
4 aces, I mean. Sorry.
Let's consider this way. Okay. Heart, we have 2 to king. Okay. The first one is 2 to king. Not heart of the ace. Ace of the heart is not drawn. And then there are 4 aces left. Okay. 4 aces. Okay? 4 aces left. This is the first case. I pick not the heart of the ace of the heart, but the 2, 3, 4 up to king. That is drawn. And then there are 4 aces left. And so this is okay. But this 13 is not okay because how many cards are there? 12, right? 12. 12 cards. There should be 12 here. Okay? Should be 12. I don't pick ace of the heart here. Okay? First try. And then there are 4 aces left. So 4 over 51. That's correct. This is the first trial. Okay. The first trial means the first case. We should consider cases. Second case is that we get ace of the heart. Okay, this is the first one. Okay, ace of the heart. And then how many aces left? 3 aces left. Right. At the first draw, we got the ace of the heart. And then necessary 3 aces are left. So what is the probability? So we have to add these 2 cases, right? They are distinct. What disjoint, I can say. This and this will not happen at the same time. So disjoint. This probability plus this probability. Okay? That's what we are looking at. Make sense? So now, first one is there are 12 hearts. Not ace, so there are 12 hearts. And we pick one of them. This is the probability. Now one card is drawn, so 51 cards left. And then still there are 4 aces, so 4 over 51. Okay, this is the first case. This case is probability this. Now, second case, we pick heart of ace. What is this probability? We pick ace of the heart.
Would it just be the 1 over 52?
Right. Okay, this is correct. Yes, that's right. Only one choice. Okay, this is only one card out of 52. Yes. And then times what? 3 aces are left out of 51, right?
Yeah.
So
3.
3 over 51. Yes, that's a probability. This is 48. This is 3. So sum is 51. Okay, this is 51. And then this is a common denominator, 52 times 51. We can cancel 51, 51. So this is 1 over 52. Okay, so this is our answer. Okay. Very interesting question, part C. First, we take heart, and then next draw is ace. So we have to consider 2 distinct cases, and then calculate each probability, and then make a sum. All right, very interesting. Okay, so we have done this. 1, 2, 4, where is it? We have done this, and then 12. 12 is done. Okay, 12 is done. And then homework 1, 3, 4 is done. Any other? Okay, looks like we have done section 1, 3. Do you have questions? Yeah, probably if you do the homework assignment, then maybe you have a question. So ask me next time. Or
Professor,
yes,
can you one more time just repeat what the 12 over 52? That one has to do with the hearts, right?
yes, because we are not picking up ace of the heart, starting from 2, 2, 3, 4, 5 up to 13, king. So there are 12 cards left. Okay, we're not considering the ace of the heart. Okay, this is eliminated. So only 12 choices. That's why we have 12 here. We're not picking up the ace of the heart this time, okay, first time. So we're eliminating hearts. So there are 12 hearts left. So out of 12, we have to choose one. Okay? So that's
So there's a total of like 13 hearts, and in that 13 there's one ace, and so,
Yes.
that's why there's a 12, because we're gonna count that like later. That's why we
yes. This is heart ace, heart the other hearts. So total of 13, right? This is one heart, ace of the heart, and another ace, other hearts. So total of 13. So we separated it into two things, ace and then others, right? 12 other cards, just one ace of heart. That one is over here, this one. All right, makes sense?
Thank you.
All right, thank you. So we're done with the section 1, 3. Okay. If you do the homework question, then maybe you have some questions. Ask me in that time. Okay. So now going to the next section 1, 4, independence. Okay. Independence. Section 1, 4, independence. Independence. Yeah, we start with the definition. Okay. Two events are independent. When? That's one. So two events, A and B, okay, these are called independent. Independent when? Simply the common event that probability of the common event A intersection B. This is a product of P of A and P of B. Okay. This is a definition. Then this case, P of A could be 0 or P of B could be 0. This could be 0, this could be 0. If this is 0, then what happens is the right side is 0, and then this probability is smaller than this probability. So this must be 0. So 0 is equal to 0. That is true. So if note, okay, note. If P of A is 0, okay, then necessary A, B are independent. Okay. Because this is 0, right side is 0, and then this is smaller than y equal to P of A, right? This probability is smaller than y equal to P of A. And then this is 0, then this is 0 too. 0 is equal to 0. This is true. So when P of A is 0, A and B are necessary independent. Or so you can say this is the case too. If P of B is 0, then necessary A and B are independent. This is a note, okay? Then one more thing, okay, one more thing. If say P of A is positive, okay, then what? A, B are independent. When? what it means. Okay, in general, okay, this is not, this probability is equal to P of A times P of A times P of B conditioned by A. Is that right? This guy, okay, this guy is equal to this. I shouldn't write over here. But anyway, the intersection of A and B, that's probability is by the multiplicative rule, P of A times P of B conditioned by A. Okay, that's the one. So A and B are independent when we can write, oh yeah, other way around. And also, okay, this is equal to P of B times of P of A conditioned by B. This is also true when P of B is positive. So, oh yeah, P of A is positive. I'm writing this guy. So probably this is true when P of B is equal to P of B conditioned by A. Okay, do you agree with this? This is true. Okay, if and only. Forget about this. Forget about this. I can prove. I can show this. Okay, I can show this. When the probability of A is positive, then this conditional probability is defined. Okay? So P of B conditioned by A is P of A intersection B, right? And then this is P of divided by P of A. Okay, so necessary P of A times P of B conditioned by A is equal to P of A intersection B. Okay. Then if independent, what happens? Independent, then this probability must be equal to P of A times P of B, P of A times of P of B. So necessarily this must be P of B. Is that right? This implies P of B must be P of B conditioned by A. Yeah. A, B are independent.
Professor, do you mind moving your notes up, please?
Oh, yes. Sorry.
Thank you.
Is the independence? Okay, independence. I'm talking about the necessary and sufficient condition for independence. So this is the definition of the conditional probability. Okay, if you use this guy, then I can clear the fraction P of A times P of B conditioned by A is equal to P of A intersection B. But if A and B are independent, what happens is this probability is a product of P of A and P of B. Okay, intersections probability is a P of A times P of B. So this should be equal to P of A times P of B. P of A is here, so this should be P of A. This is equal to P of B. That is this. So probability of B conditioned by A is equal to probability of B itself. Okay? This is what we can derive. Okay? And then other direction is, okay, other direction is, I have proved that independent, then this is obtained. And then this can be is shown in the same way. Similarly, I don't prove this. Okay. So the case when the probability of A is positive, then the independence is same as this. Okay? This conditional probability is same as the not conditional probability. Okay? Probability of B is same as the probability of B conditioned by A. But we can ignore this conditioning. That's what this is. So if you want to replace A and B or switch A and B, then we need the condition probability of B is positive. As I mentioned, when the probability of A or B is 0, necessarily A and B are independent. Okay? This is the case. So avoid this situation. Okay? Then we can say, using the conditional probability, we can say the independence. Okay, that's my point. So independence is obtained. Okay, independence is obtained. So one is this, and then other part. Then independence, the opposite to independence is dependent. Dependent. How do we define this? Dependent. Two events are dependent. When? Is there any special way? There's no special way. Simply deny the independence. Not independent. This is it. Not independent is a dependent. 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 Just like rational number and irrational number. Irrational is not rational. Dependent is not independent. That's it. So this is the definition. Okay. So independence is defined for two events when the probability of the common part, common event, is the product of each event probability. That's the definition. So then example. This is from the textbook. Red die and then white die are rolled. Okay, there are two dice, and then a red die, and then a white die, are rolled. There are two dice, and then one is red, other one is white. So those are rolled, and then we consider two events. Okay, we consider two events. The first one is event A is 4 on the red die. Okay? 4 on the red die. And event B is sum of dice is odd. Okay? Odd. So we consider this situation. Two dice rolled, red and white, and then event A is 4 on the red die, and then B, the sum of dice is odd, like 3 or 5, 7, 9, 11. Okay, those numbers. Then I would like to consider that these two events are independent or not. Okay, the question is are these guys independent? Okay, or not? So we have to check this. Are they independent or not? And how to check this? So one red die and then one white die, those are rolled, and then event A is 4 on the red die. And B is the sum of dice is odd. So are they independent or not? How to check this? We have to calculate the probability of A and then B, and then also the intersection, A intersection B. And before that, what is the sample space? What is sample space? S. Two dice are rolled. So first die, red die shows some number I, and then white die shows some number J. Okay, so I on red. Okay, I on red die, and a J on white die. Okay, white. So this is the sample space. And necessarily there are 36 outcomes. Okay? 36 outcomes. First note this. I is on the red eye and J is on the white die. Okay, so the I and J ordered pair. There are 36 possibilities. Okay, so then what is the probability A?
Would it be 4 over 6?
4 over 6?
Yeah.
Yeah, 4, I understand, 4. Really? 4? 4 on red die. Okay, 4, so I is 4, right? This case, I is 4. Then what about the J? Can this be anything? The first die is 4, yeah, definitely. But the second die, white die, can be anything, is that right? J is 1, 2, up to 6, is that so?
Nope.
Oh, it has to be odd.
No. Forget about this. Okay? We're
Okay.
just talking about A. 4 on the red die.
Uh-huh.
And then white die, we don't care. Anything is fine. Okay? 1, 2, up to 6. So that means how many elements over here? J is 1, 2, 3, 4, 5, 6. So 6 of them are here, right?
Yeah.
Yeah, so 6 out of
36.
36. Good. Okay? This is the probability.
Oh, okay.
So 4J is okay. And the J is 1, 2, 3, 4, 5, 6. So there are 6 such. This is 1 over 6. Okay, 1 over 6. The event A has the probability 1, 6. So what about the B? What do you think? Sum of the dice is odd. Okay, possibility is, oh my gosh, I don't know. Well, that's up. Okay, out of 36, how many possibility? If the first one is 1, then second white one must be 2, 4, 6. Is that right? The red one is 1. Then second one, white one, must be 2 or 4 or 6, right? If 2 is the red one, then a white one must be 1 or 3 or 5. Is that right? Do you agree?
Yes.
Yes. Up to where? Okay. Up to last one is 6. Red one is 6. Then a white one must be
1,
1 or
3,
3 or
5.
5. This is it. These are the all possible pairs. Is that right? For 1, there are 3. For 1, there are 3. For 2, there are 3.
18,
For 6, there are, yes, 15. So we have these guys.
3 times.
3 times what? 3 times 1, 2, 5, 3, 4, 5, 6. 18. Okay, 18. There are 18 such. 18 pairs. So 18 over 36. Make sense? Okay, this is equal to what? Simplify this. 1/2, right? 1/2. Probability of B is 1/2. This is the one. Now, one more thing. Probability of A intersection B. A intersection B. We need to calculate these guys. This guy, lastly. What is this? A intersection B. Okay, this is an event consisting of which kind of outcomes? First one must be 4, right? 4. red one must have 4. Then white one must have what? The sum is odd. So second one must be 1 or 3 or 5. Is that right?
Mm.
Anything else? That's it. Okay, this is it. There are only 3 pairs out of 36. So this is 3 out of 36. What is this probability? 1 over 12. Now, how do we determine A and B are independent? It is equal to the, I'm sorry, many accidents, okay, many incidents. Product of these two guys. What is the product of these two? Oh yeah, yes, this is 1/12. 1/6 times 1/2 is 1/12. Good. Okay, so what do we have? We have seen is okay. So we have seen a P of A intersection B is equal to P of A times P of B. Okay? This is obtained. This time this is 1/12. So conclusion, A and B are independent. Okay. This is the conclusion. Calculate each probability P of A, P of B, and also P of A intersection B, and then make a product of these two, and then see that that is equal to this guy or not. In this case, yes. So they are independent. Okay. So this is a way we can verify. Ah, yes, almost time. Okay. So do you have questions? This is how we verify that 2 events are independent or not. Just to calculate the each event probability and then also the intersection probability. And then see that the product is equal to the intersections probability or not. And then we can say. Any question? Okay. Please do the homework assignment, and then still you have questions, then ask me next time, Friday. Okay. You have still time. Friday midnight is a due time. So yeah, please do as many as possible. Okay. Preferably everything. Okay. Preferably everything. Don't miss any homework assignment. And that's a great. So yeah, please do. Please study hard. Any question? All right. Thank you. We'll see you next time.
All right.